Welcome back, listeners, to the deep dive. Have you ever felt that gnawing frustration when a one-size-fits-all solution just doesn't fit you?
Oh, absolutely.
Maybe it's a diet plan that works wonders for your friend but leaves you feeling sluggish, right? Or a workout routine that's perfect for a pro athlete but puts you straight on the injury list.
Yeah.
It's incredibly frustrating when a generalized solution simply isn't tailored to your unique biology, your specific needs, or your individual circumstances.
Precisely.
Right.
And this isn't just a human problem, is it? It's a fundamental challenge that extends directly to how artificial intelligence learns,
Ah, okay.
particularly in complex, dynamic, real-world environments. When AI models try to apply a single generalized policy or strategy across incredibly diverse situations or individuals, they often fall, well, dramatically short of optimal performance.
Right.
They miss the nuance, the individual variability that, defines our world.
Exactly. So that's the core challenge we're tackling today.
Right.
We're taking a deep plunge into a cutting-edge area of AI, reinforcement learning.
Specifically, a groundbreaking framework that aims to solve this very problem. We're talking about learning optimal, individualized policies from pre-collected, often messy, and incredibly diverse data.
Yeah. The messy part is key.
This isn't about finding the average solution, it's about finding your solution.
Our mission today is to unpack a recent paper that introduces the Penalized, Pessimistic, Personalized Policy Learning, or P4L framework. Bit of a mouthful, but powerful stuff.
P4L, got it.
This innovative approach directly confronts the complexities of what's called heterogeneous data in offline reinforcement learning.
Okay.
It fundamentally moves beyond the traditional and often unrealistic assumption that everyone or everything behaves in the same way.
Right, the homogeneity assumption.
Exactly. We'll explore the ingenious technical innovations at its heart and the profound practical implications that are allowing AI to truly tailor its advice, whether it's for, say, a patient's medical treatment, a robot's nuanced movement, or even a personalized financial strategy. It's about making AI work for you, uniquely and with confidence. Okay, let's unpack this then, starting right at the heart of the problem. Why does heterogeneity matter so much in reinforcement learning? Maybe a quick refresher on RL first.
Good idea. So reinforcement learning, RL, it's essentially an AI agent learning to make a sequence of decisions in an environment to maximize some cumulative reward.
Right, like learning by trial and error, but smarter.
Exactly. Think of it like teaching a dog tricks with treats. The dog, the agent, tries different actions in its environment, your living room, and gets rewards, the treats, for desirable behaviors.
Okay.
Over time, it learns the best policy, the best set of actions to get the most treats. We've seen its incredible power in things like mastering complex games like Go or chess,
Yeah, AlphaGo and all that.
optimizing robotic movements for precision manufacturing, or even developing sophisticated pricing strategies in dynamic markets. It's incredibly versatile.
Okay, so RL is powerful for learning optimal sequences of actions. But where does the heterogeneity issue come in?
Well, what's truly fascinating here, and often overlooked in the earlier days of RL, is that while it's powerful, its traditional applications often implicitly assume a kind of uniformity. They assume the dog or the environment is pretty much the same every time. But in the real world, populations are rarely, if ever, homogeneous.
Makes sense.
Consider individuals, whether they're patients responding to a drug, robots operating in slightly different factory conditions, or consumers interacting with an online store. They all exhibit substantial variations in their behaviors, their internal states, their responses to actions.
So my reaction to a drug might be totally different from yours, even if we have the same condition on paper.
Exactly. Your metabolism is different from mine. My robot might have slightly different wear and tear than its twin. Your spending habits are unique to you. These differences, this heterogeneity, are the norm, not the exception.
So the one-size-fits-all flaw here becomes glaringly obvious. If traditional RL algorithms assume a stationary and homogeneous environment, well, they're bound to come up with policies that are by definition suboptimal for many.
Precisely. They might work adequately for the average, maybe, but they won't work best for anyone specifically.
And that leads to problems, right? Like biased estimates.
Yes, it leads to biased and inconsistent estimations of subject-specific value functions. When we talk about value functions in RL, we're essentially talking about the AI's internal map of expected long-term rewards for being in a certain state or taking a certain action.
Okay, the expected future payoff.
Right. If you assume everyone is the same, your map for an individual will be inaccurate because it doesn't account for their unique terrain, their unique responses. The AI simply can't accurately predict the outcome for an individual if its underlying model believes everyone responds identically.
It's like trying to navigate a bustling city with a map that only shows the average elevation, completely useless for navigating individual streets or buildings.
Great analogy. And this isn't just an abstract theoretical issue for academics. The real-world consequences are quite profound and often quite serious.
Like in healthcare.
Exactly. The paper highlights, for instance, how ignoring heterogeneity can lead to what we call health disparities. Imagine a medical treatment optimized for the average patient.
Okay.
For someone whose biological response, genetic makeup, or lifestyle differs significantly from that average, that optimal treatment might be ineffective, or even worse, harmful.
Wow.
This is particularly true for underrepresented or vulnerable individuals whose data might be less dominant in that average calculation.
Right, their unique needs get smoothed over.
Similarly, in robotics, a generalized policy might make a robot less adaptable or efficient when faced with slight variations in its operating environment or task. A robot trained on pristine factory conditions might struggle with a bit of dust or a slightly misaligned component.
So it lacks robustness to individual differences.
Precisely. This underscores the critical need for individualized policies because the stakes are high, whether it's a person's health or a robot's performance.
That makes the "why should I care" moment incredibly clear. So if one size fits all is failing us, what's the real culprit when it comes to AI? Before we dive into this new P4L solution, maybe let's look at how people have tried to crack this code before. It's always good to understand the landscape.
Absolutely. Understanding previous attempts really highlights the innovation here. One approach mentioned is personalized simulators, or PERSIM.
PerSim, how did that work and what were its limitations?
PERSIM was an interesting attempt. The core idea was to learn a personalized simulator for each individual. Think of a simulator as a kind of digital twin.
Okay, like a virtual copy of me.
Sort of, yeah. One that can predict how an individual will respond to different actions. So PERSIM tried to create a unique digital twin for every patient, every robot, based on their unique characteristics. It assumed a low-rank tensor structure of latent factors for each individual state and action, basically trying to model how each person's environment or internal dynamics might differ.
Sounds complex, but potentially powerful. What was the catch?
The key limitation was a big one. It requires a finite state space.
Finite state space.
Yeah, and that's a major constraint because many real-world scenarios, especially those involving continuous variables like patient vital signs, blood pressure, or complex robot sensor readings, have vast, effectively infinite state spaces.
Right, you can't just list out every possible blood pressure reading.
Exactly. If you can't represent every possible state, your simulator becomes, well, less useful in practice. It simplifies the problem in a way that often doesn't hold up.
That sounds like a fundamental restriction. It's like trying to map the entire ocean but only having enough ink for a puddle. What about methods that tried to cluster individuals, like the group-wise policies? They seem to acknowledge heterogeneity by dividing people up.
I certainly do. These methods recognize that individuals can often be grouped into similar clusters, and they attempt to learn separate policies for each identified group.
Okay, so find groups. Learn a policy per group.
Right. For example, some focused on heterogeneity, mainly in the reward function, learning queue functions and groups simultaneously. Then they updated policies on a group-wise basis. Others used techniques like change point detection to identify group-wise policies.
But what was the limitation there? Sounds logical.
The surprising fact here, and a critical limitation, is that while they recognize heterogeneity in cluster, they often ignore information borrowing among groups.
So they don't learn across the groups.
Generally, no. It means that data from one group isn't fully leveraged to inform the learning for another, even if there are subtle similarities between the groups. You're essentially treating each group as a completely isolated silo.
Okay, I see.
This leads to sample inefficiency because they don't fully utilize the collective data from the entire population. You're throwing away potentially useful information that could bridge gaps between groups.
Like having separate libraries for each subject in a school, never allowing students to cross-reference books from other subjects even if they're relevant.
That's a good way to put it. It seems like a missed opportunity.
Definitely. And what about meta-reinforcement learning, or meta-RL? That sounds incredibly promising for diverse tasks.
Yeah.
Learning how to learn across different contexts. We hear that term a lot.
Yeah, MetaRL aims to learn a policy that can maximize rewards across a distribution of heterogeneous tasks, which sounds perfect for this problem, right?
Seems like it.
The idea is to quickly adapt to new, unseen tasks based on prior experience with similar tasks. However, for offline data, which is the focus here, data that's already collected.
Right, no interacting with the environment.
Exactly. For offline data, MetaRL faces significant practical hurdles. It typically requires the collection of millions of interactions with environments during meta-training online or more pre-collected training data.
Which you just don't have in an offline setting.
Precisely. Think about it. If you're working with historical patient records, you can't go back in time and run new experiments. This makes MetaRL less feasible for many real-world scenarios where online interaction isn't possible or where existing data sets might be limited in scale for individual tasks within that meta-learning framework.
Okay, data hungry, especially online data. Any other issues?
Well, furthermore, the theoretical understanding of offline meta-RL remains limited, meaning the robust mathematical guarantees we often seek for these algorithms are still developing. It makes it harder to predict their performance with certainty.
So massive data requirements, especially for online interaction, which often isn't available, and less theoretical backing for the offline setting. Got it. And finally, there's heterogeneous treatment effect, or HTE. This sounds highly relevant to personalized medicine.
HTE is indeed crucial for personalized treatment regimes. It's all about figuring out which treatment works best for which patient based on their individual characteristics. Like predicting if a certain blood pressure medication will be more effective for a patient with a specific genetic marker.
Okay, sounds very close. What's the difference?
The crucial distinction is HTE generally focuses on a single decision point.
Just one choice.
Right. You choose a treatment once, observe the outcome. Reinforcement learning, by contrast, deals with sequential dynamic decisions over time.
The sequence matters.
Absolutely. You choose an action, observe the outcome, the environment changes, and then you choose another action based on the new state, and the sequence continues. This sequential nature introduces complexities, like the impact of current decisions on future states and rewards, that HTE alone doesn't address.
It's the difference between picking the best car for a single trip versus navigating a complex, ever-changing journey with multiple stops and evolving conditions.
Perfectly put.
So to summarize these existing approaches, what were the core fundamental challenges that remain largely unsolved, that kept truly personalized AI just out of reach in the offline setting?
The paper pinpoints several critical unaddressed challenges that P4L aims to overcome. First, the reality is that each individual subject often has different state action transitions and receives different immediate rewards.
Right, the inherent variability.
This makes a single global model problematic. Two patients with the same diagnosis might respond very differently to the same medication dose, leading to different subsequent states and outcomes.
Okay, fundamental heterogeneity. What else?
Second, when traditional batch RL methods assume subject homogeneity and try to learn a common, optimal policy for everyone, they inevitably lead to biased and inconsistent estimation of subject-specific value functions.
Resulting in suboptimal policies, as we say.
Exactly. They smooth over the unique bumps and turns of individual journeys.
And even when they tried to cluster and learn group-wise, they still diminished sample efficiency because they weren't incorporating cross-subject information in policy learning, right? They were still working with isolated pockets of data.
Precisely. And this leads to the third major challenge, the distributional shift.
The distributional shift. Let's unpack that.
Okay, so in offline RL, you're working with pre-collected data from some fixed behavior policies. You can't interact with the environment to explore new states or actions.
Like learning to drive from a dash cam recording, you only see where that specific driver went.
Right, you can't suddenly turn left if the driver only ever turned right. If your target optimal policy wants to visit states or take actions that are sparsely represented or not seen at all in the collected data, especially for a specific individual, you face a significant problem.
Because your data doesn't cover the paths you want to take.
Exactly. This distributional shift between the observed data's behavior policies and the desired optimal policies dramatically increases estimation errors and causes suboptimality in learning. It's like trying to navigate a new city with an old, incomplete map where many crucial roads are missing, particularly the ones you need to take.
You're going to get lost, and your AI is going to make poor decisions. That makes perfect sense.
Yeah.
You're always trying to make decisions based on data that might not fully represent the optimal path for an individual. It's a huge blind spot.
It really is.
So this brings us to the proposed solution, the P4L framework: penalized, pessimistic, personalized policy learning. How does it tackle these complex, stubborn issues? What's the central innovation?
Okay, the aha moment with P4L is its innovative heterogeneous latent variable model.
Heterogeneous latent variable model.
Okay. Instead of learning completely separate models for each individual, which is data intensive, or rigidly clustering them into distinct isolated groups, P4L introduces a shared structure on policies and queue functions with latent variables.
Shared structure with latent variables. What are these latent variables like?
Think of these latent variables, denoted as U, as unique hidden identifiers for each individual's quirks and characteristics. They're like secret genetic markers or personalized dials that subtly adjust how the core model applies to a specific person.
I love that analogy. So like a shared recipe for cookies, but each baker, representing an individual, has a slightly different secret ingredient that makes their cookies uniquely delicious.
Exactly.
The framework finds the common recipe while accounting for these individual tweaks. This sounds like it perfectly bridges the gap between treating everyone identically and treating everyone as completely isolated.
Precisely. It's a powerful sweet spot. This shared structure encourages the grouping of individuals with similar latent variables, which naturally leads to similar optimal policies for those within the same subgroup, all without explicitly predefining those groups in advance.
So it discovers the groups implicitly.
Yes. Going back to our cookie analogy, the fixed effect is the universal part of the recipe: flour, sugar, eggs, the same for every batch. But the random effect, that's the personalized twist.
The secret ingredient.
It's the unique blend of spices or the specific type of chocolate chip your baker adds, making your cookies distinctly yours, while still being fundamentally cookies from the same base recipe.
Okay, and how does this look mathematically? The paper mentions a specific model.
Right, they give a concrete example. For Q functions, they use a linear mixed effect model. Here, Q represents the shared fixed effect, the general recipe, and U captures the individual specific random effect, that unique secret ingredient.
Got it. Fixed effect plus random effect.
This elegantly combines the efficiency of a shared model with the flexibility of individual customization. It's about finding the commonalities and the differences simultaneously, maximizing the use of all available data.
That sounds like a powerful way to leverage collective data while still respecting individual variations. But what about the data coverage problem? The distributional shift you mentioned earlier. That's a huge issue in offline RL.
Indeed, the distributional shift is a significant hurdle. If your target optimal policy wants to visit states or take actions not seen in your own individual data, you're stuck, as we discussed.
Right.
P4L introduces a very clever solution called the partial coverage assumption. This isn't just a tweak. It's a really key shift in thinking.
Partial coverage assumption.
Yeah.
Okay, how does that work?
Imagine trying to teach a student using only the books they've personally read. Incredibly limiting. Now, imagine if you could leverage the entire library of knowledge from all students to fill in the gaps for that specific student.
Okay, pooling the knowledge.
P4L's partial coverage does exactly that for AI. Instead of requiring each individual's data to fully cover every possible state action pair that their own optimal policy might visit, P4L only needs the grand average visitation probability of the batch data from all individuals to cover the discounted visitation probability induced by the target policy for each individual.
Whoa, okay, unpack that slightly. The average coverage from everyone needs to cover the target for each person.
Exactly. This is a key innovation. It means the state action pairs induced by a target policy for individual idocia can be covered by behavior policies from any individuals in the population.
So you're essentially borrowing information from others. That sounds like a much more realistic assumption in practice than expecting each individual's limited data set to be exhaustive.
It absolutely is. It transforms limited individual data into a collective treasure trove. This isn't just more realistic, it's what makes personalized AI truly scalable.
Because you don't need perfect data for everyone individually.
Exactly. This allows for what they call borrowing information from other individuals, which is absolutely crucial for sample efficiency, especially when individual trajectories might be short, sparse, or incomplete.
Makes sense.
It means if one individual's data is lacking in a certain area, the collective experience of others can help fill that gap, allowing for a much more robust policy to be learned for that individual. It makes the entire framework much more practical.
Okay, so we've got a smart way to model heterogeneity and a more realistic collaborative data coverage assumption. What about the pessimistic policy learning strategy? Why the emphasis on pessimism? That sounds counterintuitive for an AI trying to optimize.
Yeah, it does sound a bit odd, doesn't it? But pessimism here is not about being negative. It's about being robust and confident in an uncertain environment.
Okay, robustness. How?
In offline RL, there's inherent uncertainty because you're inferring policies from fixed data. You can't actively experiment to confirm your assumptions. The method optimizes the policy by using the most pessimistic Q function estimate from a set of possibilities.
So it looks at the range of possible outcomes and assumes the worst.
Kind of. It's deliberately choosing the Q function estimate that gives the lowest expected value given the data and the model uncertainty. It's like preparing for the worst case scenario within the bounds of what the data tells you.
Okay.
This ensures that the lower confidence bound of the values of learned optimal policies is the largest among all in-class policies. It's like finding the best strategy even if things go slightly wrong.
So you get a strong guarantee.
Yeah.
Like it will perform at least this well.
Exactly. It gives you a reliable floor rather than gambling on the most optimistic outcome, which might fail spectacularly if your estimates were off. This strategy also can relax the full coverage assumption even further because it inherently accounts for uncertainty where data might be sparse. It's a powerful safeguard.
That makes a lot of sense. You're building in a safety net. Now, for the technical wizards out there, how do they handle the computational side of this? The paper mentions a dual problem and multi-centroid penalties. How do these make P4L efficient?
Right. The original optimization problem for P4L is quite complex. It's difficult due to the constraints on Q and the need to maximize over policies and latent variables simultaneously. Think of it like trying to solve a Rubik's Cube blindfolded with one hand tied behind your back.
Okay, pretty hard.
Very. To address this complexity, the paper employs a common and powerful technique in optimization, solving a Lagrangian dual problem.
The dual problem. Don't need all the math, but what's the gist?
Conceptually, it's like transforming that blindfolded Rubik's Cube into a different puzzle that, while looking different, is far easier to solve using standard techniques. It turns a constrained, difficult optimization problem into an unconstrained, more manageable one.
Making it easier to compute.
Much easier, often solvable with standard optimization techniques like stochastic gradient descent, leading to much more efficient computation.
Okay, that handles the main optimization. What about the multicentroid penalty? That sounds specific to grouping those individual latent variables, the UTSWIs.
It absolutely is, and it's a key to P4L's efficiency. This penalty term encourages latent variables U for individuals within the same subgroup to be similar to a central point, a centroid VK.
So each subgroup has a kind of center.
Exactly. Imagine you have K potential subgroups, and each subgroup has a central VK that represents its ideal U, its unique secret ingredient combination. The penalty pushes each individual's U closer to its nearest VK.
And why is that good?
It has multiple benefits. First, it significantly reduces the computational complexity to ONK compared to ON2 for other methods that might compare all pairs of individuals.
And individuals, K subgroups. K is usually much smaller than N, right?
Exactly. Think thousands of individuals, but maybe only 5-10 distinct subgroups.
Yeah.
So ONK is a massive computational saving compared to ON squared.
Huge difference.
Second, it reduces estimation bias compared to simpler penalties. It's a smart way to induce subgrouping without incurring huge computational costs or compromising accuracy, making large-scale personalization feasible.
That's a powerful combination. Smart modeling, robustness through pessimism, and computational efficiency. What about the theoretical guarantees? What does the math say about how well this actually performs? How can we trust it?
Right. This is where we look at the regret metric. In RL, regret is crucial. It's essentially the value loss of the estimated policy compared to the true optimal policy.
How far off are you from the best possible outcome?
Exactly. The goal is to make this regret as small as possible, ideally converging to zero as you get more data. The paper lays out rigorous theoretical foundations to back its claims.
What kind of assumptions do they need to make for those proofs to hold? Complex models usually need some conditions, right?
Indeed. The technical assumptions underpin the theory. One key assumption is boat mixing.
Beta mixing.
Yeah, it essentially means the data isn't too correlated over time, Dependency between observations decays quickly. Like, a patient's vital sign now is related to the reading from 2 minutes ago, but the influence of a reading from 2 days ago quickly fades.
Okay, limits long-range dependencies. Makes sense. What else?
Then there are covering numbers and Lipschitz conditions, which are mathematical ways to ensure that the complexity of the function classes used, like for policies or Q functions, is controllable, not infinitely complex.
Keeps the math tractable.
Right. And finally, there's the realizability assumption, which basically states that the true Q function can actually be modeled reasonably well by the chosen function class. Your model needs to be capable of representing the underlying reality.
Okay, standard stuff for these kinds of proofs. So, with that groundwork laid, what are the key theoretical results? What's the proof in the pudding that P4L works?
They deliver strong oracle regret bounds. It proves that P4L's regret can converge to zero at a remarkably fast rate near ONT.
Okay, N is individuals, T is trajectory length. What's significant about that rate?
What's really remarkable is how efficiently P4L learns. Its error rate improves dramatically, not just with more data per individual T, but especially with more individuals N in the dataset.
Ah, so more people really helps.
Yes. It effectively borrows intelligence across the entire population. This rate scales reversely with the number of individuals N because our algorithm uses all information from N individuals through a shared structure. That's a major advantage over methods that don't share info effectively.
So it really leverages that shared structure to speed up learning across the entire population, even if we don't know the true subgroups beforehand. That sounds incredibly powerful.
It is. Furthermore, they establish asymptotic oracle consistency.
Meaning?
This means that even without knowing the true subgroups in advance, the method can learn a pair, well, which can be as good as the oracle pair, in terms of the regret asymptotically.
So eventually it performs as well, as if it magically knew the true groups from the start.
Pretty much. It's a robust result, indicating the algorithm is capable of discovering and utilizing those latent subgroup structures on its own, based purely on the data. It figures out the secret ingredients and how to group the bakers all by itself.
That's fascinating. It discovers the patterns of individuality. Is there a catch? Any technical conditions that might limit its application, maybe with deep learning models?
There is a notable point regarding the dual problem we discussed. While it offers computational elegance, achieving these strong theoretical guarantees sometimes requires the convexity of the Q space.
Convexity.
This technical condition ensures there's no duality gap, meaning the dual problem solution matches the original problem solution. However, in modern deep learning, Q functions are often represented by deep neural networks.
These are definitely not convex.
Exactly, they're highly non-convex. This raises an important question for future research. How do these theoretical guarantees hold or adapt when the Q space is non-convex? It highlights the constant tension between rigorous theory and powerful practical deep learning models.
That's a great point for future work and crucial for deploying these in complex real-world systems. Now let's bring this to life. How does the P4L algorithm actually work in practice, step by step?
Okay, let's talk algorithm 1 from the paper. It's an iterative process, refining its understanding over many cycles. In essence, it updates the function approximations for the features, f, the Q values, q, and the policy using stochastic gradient descent.
Standard machine learning optimization.
Right. You update parameters based on small batches of data, nudging the model towards better performance. The trickier part is handling the latent variables, u and v, those individual quirks, and their subgroup centroids.
How does it manage those?
For these, it uses a method called the alternating direction method of multipliers, or ADMM.
ADMM. Sounds fancy.
Think of ADMM as a clever way to break down a big optimization problem into several smaller, easier subproblems tackled in sequence. In P4L's case, this method relies on k-means clustering to manage those multicentroid penalties we discussed, effectively grouping similar individuals together in the latent space during the updates.
So it's constantly refining the core functions and figuring out the individual latent variables and their subgroup assignments simultaneously.
Clever. And how do they decide on k, the number of subgroups? Do you just guess?
Good question. It's a practical consideration. The paper suggests a heuristic, selecting K by first clustering individuals according to their stationary transitions.
Meaning?
Essentially, you estimate how each individual's state-action dynamics behave, how they tend to move from one state to another given an action, and then you group those with similar dynamics using something like k-means. This gives you an informed starting point for K.
Okay, so you're not just guessing. You use a preliminary analysis of behavior to set the stage. Makes sense. So with the algorithm in hand, what did the simulation studies reveal? Did P4L live up to its promise against existing methods?
They ran two main simulations. First, a simple environment with a balanced design and three distinct predefined groups of individuals, each with different state transition parameters. A clear, controlled test of heterogeneity.
And the results? Quite compelling. P4L and ACPI, another clustering-based method, clearly outperform other methods for homogeneous data, like FQI and V-learning, which assume everyone's the same.
As expected. But how did P4L compare to ACPI?
The surprising fact was how much better P4L performed, especially when K was correctly specified. Crucially, P4L also showed smaller variance than ACPI.
Smaller variance. Why is that important?
It means P4L's performance is more stable and reliable. This happens because P4L efficiently borrows information across subgroups through its shared latent variable model. It learns more robustly with less data. ACPI, learning within each cluster, isolates data and loses that collective wisdom, making it more sensitive to noise or limited data in a specific cluster.
So P4L's ability to borrow information gives it a significant edge in sample efficiency and stability.
Got it. What about a more complex scenario, like the OpenAI Jim cart poll environment? That's a classic control benchmark.
Right, the cart poll. The goal is to keep a pole balanced on a moving cart. They introduce heterogeneity by varying the length of the pole and push force, simulating different types of carts. So different physics for different individuals.
Exactly. The results again showed that P4L outperforms the benchmarks when K is chosen appropriately. And just like before, ACPI usually suffers from a larger standard error than ours, again highlighting P4L's superior sample efficiency and robustness.
And even if K wasn't perfect.
Even when K was selected heuristically, P4L performed remarkably well, confirming its practical utility beyond idealized settings. It shows P4L holds up in more complex, dynamic environments.
Those simulation results are strong indicators. But the true test is real-world, messy data. How did P4L fare when applied to treating sepsis using the MIM3 data? The stakes there are incredibly high.
This is where it gets really impactful. Sepsis is a severe, life-threatening medical condition. Optimal treatment decisions, especially about vasopressors and intravenous fluids, are crucial.
And the MIM3 dataset.
It's a comprehensive, publicly available dataset with longitudinal information collected from 17,621 patients in ICUs, vitals, labs, demographics, clinical scores like the SOFA score, a goldmine of real-world patient data.
17,000 patients. That's huge. But medical data is notoriously complex. How did they prepare it for an RL algorithm?
Data prep was key. The original state space was 41-dimensional, lots of numbers. They used a dimension reduction procedure via principal component analysis, PCA.
PCA, okay, to simplify it.
Right. It condensed the data into a more manageable 11-dimensional encoded state. The top 10 principal components plus the patient's SOFA score. The SOFA score, assessing organ function, is a direct and clinically meaningful measure of sepsis severity.
Makes sense to keep that explicitly. What about actions and rewards?
The actions were discretized combinations of vasopressor and IV fluid treatments, giving an action space of size A9. The reward function was chosen as the negative SOFA score at time t+1.
So the goal is to minimize the future SOFA score, improve patient condition.
Precisely. Learn treatment policies that lead to a better patient state.
How did they evaluate these policies? You can't just test them on real patients retrospectively, can you?
No, that's the big challenge with real clinical data. Since the true optimal outcomes aren't known, they used a clever workaround. PERSIM, a state-of-the-art method to estimate personalized simulators, to evaluate the learned policies.
Using those personalized simulators we discussed earlier as a testing ground.
Exactly. You learn a simulator that approximates how individual patients would respond, and then you use that simulator to evaluate your learned policies in a hypothetical yet realistic scenario. It's the next best thing to actual clinical trials for offline evaluation.
Clever. And what was the bottom line? How did P4L compare in this high-stakes sepsis scenario?
The results were highly impressive. P4L outperforms the others in terms of value, a cumulative discounted negative SOFA scores, indicating it leads to better decisions in the treatment of sepsis.
Better than other algorithms. What about doctors?
What's particularly striking is that even clinicians' decisions, the real-world benchmark, were second to that of our method and with the lowest variance.
Wait, P4L did better than the clinician's recorded decisions on average in the simulator.
According to the PERSIM evaluation, yes. The lower variance for clinicians' decisions is expected, of course, because there's no mismatch between their behavior policy, what they actually did, and the target policy being evaluated.
Right.
In contrast, methods like V-learning and FQI, which ignore heterogeneity, performed poorly. ACPI did slightly worse than clinicians and had larger variance due to its reduced sample efficiency. P4L came out on top.
Wow, that's a powerful validation. It suggests P4L can genuinely learn personalized treatment policies from diverse patient data that could potentially lead to better outcomes.
It's a strong demonstration of the potential for precision medicine driven by this kind of sophisticated RL.
So to recap, P4L is a significant achievement, a novel RL framework for individualized policy optimization from heterogeneous offline data. It offers that fast average regret rate under a weak partial coverage assumption, making it much more practical.
Absolutely. It's a leap forward in making offline RL applicable to complex, diverse, real-world problems where heterogeneity is the norm. It moves us closer to AI that genuinely understands and adapts to the individual.
But what's next? The paper itself points towards future work, right? Where does this research go from here?
Always good to look ahead. The paper is quite insightful about exciting future avenues. One key area is pushing the theoretical boundaries further.
Like relaxing assumptions even more.
Exactly. Can the partial coverage assumption, already a big improvement, be further relaxed? This raises an important question for advancing the theory, perhaps using more advanced stats techniques to handle even sparser data.
Pushing the limits of data constraints.
Right, and we touched on this earlier, but what about those non-convex Q spaces common in deep learning?
Can the theory handle deep neural networks?
That's the question. Investigating if the theoretical guarantees still hold, or if the duality gap is negligible when Q is non-convex is crucial. Bridging this gap connects strong theory with the most powerful practical tools.
And what about understanding the fundamental limits? How good can we possibly get?
That falls under investigating theoretical challenges of establishing regret lower bounds for offline RL with heterogeneous data. Knowing the theoretical best possible performance helps guide future algorithm development. It sets the bar.
Makes sense. Beyond theory, what about practical deployment? What happens when a new individual shows up, someone not in the training data?
That's a critical practical step. Future work needs to explore how to apply these learned policies to a new individual not in the pre-collected data.
How would that work?
Yeah,
Quickly learn their E.
likely something like that. Efficiently getting just enough new info for that individual, maybe a few initial observations, and then quickly classifying or adapting them into one of the learned subgroups to apply the most relevant policy. That's the challenge of true generalization.
And environments change, right? People's conditions evolve.
Absolutely. The current framework focuses on time-stationary heterogeneous MDPs. It assumes individual characteristics and dynamics don't change over time.
Which isn't always true.
Right, so future research needs to address time non-stationary heterogeneous episodic MDPs. This would enable policies to adapt dynamically to evolving individual behaviors or environmental shifts essential for long-term deployment.
And finally, what about even more complex real-world variables, things the model might not capture yet?
The paper points to exploring optimization with unmeasured confoundings, hidden variables affecting treatment and outcome, but not recorded.
Tricky stuff.
Very. Also, alternative types of rewards, such as time to event. Instead of just optimizing a SOFA score, maybe optimize for time to recovery or survival duration. These are more nuanced aspects, pushing personalized AI into even more sophisticated domains.
This deep dive truly shows us the incredible potential of AI that learns to understand and adapt to individual differences. It makes me wonder, what other areas of our lives could be revolutionized? Personalized education, financial advice, tailored to you based on your patterns.
That's a powerful vision.
This shows that future isn't just a dream, but a rapidly evolving reality built on innovations like P4L.
Exactly. Understanding and effectively modeling heterogeneity is absolutely key to unlocking truly impactful AI across countless fields.
That's all for today's deep dive. We hope this exploration into personalized reinforcement learning gave you some exciting new insights. To stay updated on the latest AI and ML research papers, visit our webpage linked in the show notes. Join us next time for another deep dive into the cutting edge of AI.